associate professor here in materials physics at Michigan University. This is a boot camp, and I will talk about 3 hours or a little less than that about measurement uncertainties and fundamental concept of statistics. I'm talking about this because there is one fundamental research question that most researchers actually is working on, and that is my modified device performing better than my reference device? I mean, you do some kind of improvement of materials in your research or something, and you want to prove that, right? So how do you do that? In a scientific way, in a significant way, as I say, statistically significant way, if I'm very detailed. So yes, this is mandatory knowledge if you call yourself PhD students, and also if you're a senior scientist as well. And I will work by giving examples from the electrochemical battery cell performances. Those kind of tests. And there are way too many published papers in this field that are making conclusion based on just a single cell or sample being tested and evaluated. So now we're going to change this. Yes, I made this PPT in phone portrait format, and this is because you should have easy accessibility and can look on this on the phone every single time you go to the lab or something like that, because this is really important. And I have seen that 95% of you all out there with 95% confidence interval, to use some fancy word here, doesn't understand these basic concepts of statistics and measurement uncertainties. And to give you an example of that, if you belong to that group, I have these 4 deadly errors, as I call them. If you answer yes to any one of these and you feel that you can recognize in them, then you are part of this. So the deadly error number 1 is that if you say, yes, if I just be more careful with my measurement, then they will improve and everything will become exact values. Yeah. And if I repeat the measurements and if I'm really careful when I'm repeating it, I will get the exact numbers, same digits on my measurement. And then we have deadly error number 2. If you say, yes, I just need more digits on my scale, then the measurement will improve, of course. The measurements uncertainties I'm always experiencing, that is just caused by poor equipment. So if I just increase the digits, the resolution of my measurement scale, then everything will improve. Deadly error number 3. If you say, yes, I just subtract the mean value from my references test, and then I use those in my single samples that I'm testing. Because I heard that mean values, that improves accuracy. So that should be the way to go, right? Deadly error number 4. If you say, yes, I only measure one sample pair. I mean, I make a device, the reference device, test its performance, and then I make another device and test that I have done my modification on. And if that modified device performs better, well, that proves my thesis, right? I mean, it just has to be larger, then it's good to go. And if it sometimes, it can actually happen, I have seen that it doesn't show improvement. It can actually be a negative thing sometimes, that it performs worse. But that is, of course, caused by some kind of measurement glitch of the equipment, or me that has forgot to think about a certain parameter or something. So then I just redo it in that case. So if you answer yes to any of these 4 questions, then you really need this PPT, because these are very critical errors actually. And then you should look on this PPT every day you wake up and every day you go to bed for the rest of your PhD time remaining. I'm trying to sort of pull, what shall I say, a hard string here, and then try to make you really take this serious. I mean, way too many students downplay this concept. Statistics is known to be boring in some way or complicated. But stay with me on this and you'll learn something. So after this presentation, this boot camp, you should be able to understand why you shall measure 5 repeated experiments. You will learn how to compensate with something called student t-correction for that low number of samples. Yeah, 5 is a very low number. Ideally, 100 is considered a good target. And those of you that only do 1, I will not comment further on that. You will also understand that there's a difference between the concept standard error and standard deviation. I bet most of you doesn't even know there's something called standard error at all, or perhaps you believe they are the same. You will also learn that there's a difference between mean values of sets and the standard errors that goes together with them, and single samples and standard deviations that connects to the single sample domain. You will also understand that you shall not mix single cell data and mean value data within the same calculation. And you will understand why that is bad. You will also learn and how to actually do a comparison test. I mean, that kind of before and after modification to prove if it is statistically significant. And we want to do that at a 95% confidence level, as we say. A proper mean value A minus B test, so to say. And we will learn when to use 68 or 95% confidence interval as well, and what confidence interval is at all. So here's a table that describes how the student tend to believe what type of phenomena influences the measurement uncertainties, and how that relates to how it is in reality. So I made this table to make you reflect on how the contrast between these two things really are. So the first example of a phenomena contributing to the measurement uncertainty, that is the electronic measurement devices, like multimeters or potentiostats and things like that. These students believe to have a great influence, like 50% at least. And in reality, these electronic devices is really accurate. I mean, it's amazing how good they actually are. So you can see that they have the least contribution in reality. The reason why the students tends to think it has high contribution, I believe it is because that measurement device is seen as some kind of mysterious black box. They don't really know how the electronics works on the inside of the instrument, and that, what shall I say, uncertainty they feel about the equipment is reflected how they judge the measurements uncertainty of the equipment becomes. And then we have the second phenomena, which is the operator's own mistakes. The doubt in oneself when you're doing lab work, basically. And students also tend to believe that has a great influence. I mean, they think that the measurement uncertainty that they have in their data is caused by they being clumsy in the lab, that they forget to write down the numbers correctly, or that they do other types of mistakes and things like that. So, and that is a complete misconception. I mean, in reality, that's very rare these kind of things happen. So that has a very small influence, I would say. And then we come to the third phenomenon here, which is like the turning point when things start to become serious in reality. And that is the design of the experiment. These students, on the contrary here, tends to downplay. They think that the design of the experiment is like, how hard can it be to do a measurement, right? They tend to have that attitude. But then when they actually are doing the experiment, then they find out that they haven't talked it all the way through. They do some tests on Monday, and then they are supposed to continue on Tuesday, but then something was missing on Tuesday, or the chemicals that they used have degraded overnight, and then they need to redo the batch, and things go on like that. That starts to creating a greater influence on measurement uncertainty than they actually tend to believe. The fourth example is improper handling of measurement equipment. That means you actually uses the equipment in the wrong way. What I'm meaning by that, if you take like the multimeter, for example, you're going to measure voltage with the multimeter, and let's say it's a very small voltage, like in millivolt range, and then you set the range on the multimeter to 100 volt. So technically it is still measuring voltage, but you have the wrong range, so the resolution of that measurement device becomes too poor for the task. These things the students tend to miss. They don't reflect on this. And this has actually a great influence on measurement uncertainty. And then we come to the last example, and that is the experience of experimental methods and the interpretation of the results that you achieve from them. And here there is a too naive approach to realize the complexity found in measurement tasks. It's this thing that, how hard can it be thinking again? And here the experienced persons know the idea behind material-related uncertainties. That you're working with research-grade chemicals and things like that. You know that you benefit a lot in the results, the uncertainty of the result, if the input data is as well defined as possible. If you simplify the experiment as much as possible. Because you know, if you have experience, that the outcome on the other side of these measurements tend to be very tricky data sets. So that actually has the largest influence of the measurement uncertainties, and students tend to downplay that a lot. The error one then. So the error one was if you said, yes, I just need to be more careful when I'm doing my measurements, and then they will improve. They can even become exact values. All right, that was the deadly error one. If you are in that case, you haven't learned the basics of measurements and fundamental, experimental concepts and general ideas about statistics. So it's not about, students tend to believe that it can be caused by the student being lazy. Reading these numbers on the scale poorly, or they have bad experimental practices and so on. The measurement uncertainty is not caused by the student. You must understand that this is something that is a fundamental thing of reality itself. So it's not about you this time. And you must understand that every single measurement that you do, every single result that you publish, you must have a value of its uncertainty alongside it as well. Because measurement uncertainty is a thing of reality itself. Otherwise, your result will be worthless. It will not be scientific. And there is a very basic understanding actually around this, because you want other researchers to be able to build on your result. And one can only build on another one's result if you know how the uncertainty connects to it, right? It's like you're building a bridge. Some guy says to you that they have measured the distance across the bay to be 1,053 meters. Then you need to decide how long shall the bridge actually be. And then you need to know how accurately is that distance across the bay. Shall you make the bridge 1,053 meter, 1,100 meter, or 1,200 meter? That is the thing I'm talking about here. So it doesn't mean that it has anything to do with you. But still, many people do, things that is wrongly by themselves. They can have issues like measuring poorly on the scale and so on. But that is another thing. Okay, deadly error 2. So that was if you said, yes, I just need more digits on my scale, then measurements will improve. So if you are in that case, you haven't learned the basics of measurements and the fundamental experimental concept yet either. So here I have a table. Let's look on this. It's two different weighing scales that have different precision. And these are data sets of 100 samples, but we only have 5 samples presented here in the table. And we can see that the first scale has 0.1 milligram in resolution. So that's a pretty good lab grade scale, right? We see 46.0 milligram, 46.1, 45.9, 46.0, 47.2. So there is some kind of variation here in the data, right? And then we do the same measurements, 100 measurements, same samples, but with a much more precise scale. This has the resolution of 0.001 milligram. So that means we get 5 significant digits this time. 46.012, 45.987 milligram, 46.008, 46.035, and 45.975. So these are just 5 samples taken from those 100 measurements. So if we do some statistical calculation on this, we can calculate the mean value m, right? And usually we write that in statistics with these angular brackets. So angular brackets around the m means the mean value. And in this case it becomes 46.003 milligram. And then we can calculate something called the standard error, which is in this case 0.040 milligram. So 0.040. And this we tend to write in combination in a short way. So we write it as 46.003 brackets 40 milligram. So when we write brackets like that, we mean that that's standard error is correlated to those 2 last significant digits of the actual mean value. We will come back later to what standard error and standard deviation actually is, but just let's continue and stay with me here. The standard deviation in this particular case becomes 10 times larger. The sigma value, as we call it, becomes 0.40 milligram instead of 0.040, which was the standard error. So standard deviation is the expected spread in single samples. So the standard deviation is what we see here in the table, how much the number fluctuates, right, in the data set. And since the standard deviation is 0.40 here and this resolution of the scale is 0.1 milligram, that simpler scale captures that spread pretty good. So here comes the point. If I use that simpler scale, which is actually a pretty good lab grade scale here, that one costs $2,000. If I upgrade and chooses that with 5 significant digits with resolution 0.001 milligram, that scale is quite advanced, I would say. It will cost you $50,000. So you need to choose where to spend your money here, right? But besides the money you invest here, there is also the time. If you're going to take 100 measurements on a scale, writing down 3 digits for each measurement will take half the time compared to if you need to write down 5 digits for each sample, right? So my point here is that a more expensive scale with higher precision doesn't improve the uncertainty of the measurement, because the measurement uncertainty is caused by variation within the sample themselves. And this phenomena is key that you understand from now on. So how do I know if my instrument has enough resolution or digits on the display? And we work with scales in this presentation, but this is a general thing, goes for all equipment. So what we have here on the presentation is a histogram, as it is called. A histogram is something where you collect your number of measurements into boxes, as we say. And the boxes is the height of the box is the number count of measurements that we have within that box. And on the X scale, we have the physical quantity that we're actually measuring. And for the scale, it is mass. So we have mass in milligrams here. So if you take 100 measurements and then you create this kind of histogram, you see that they tend to align themselves up in a symmetrical way here. And they align themselves symmetrically around what we call the mean value, right? And if you look on that black line there, that solid line is what we call a bell-shaped curve. So if the boxes that we have, the width of the boxes here is 0.1 milligram, which is the resolution of the scale that we used. So if we count the number of boxes, we see that we can get about 12 boxes that fits inside that bell curve shape. So if we have that amount of boxes, that means we are in a pretty good shape that this scale we're using can accurately resolve that measurement uncertainty that we're having in the samples. On the other hand, if you would only have 3-4 boxes inside there, because it's a very narrow shape distribution, then you probably need to upgrade your equipment. But only then. So give you some kind of numbers on this. I can say that the lowest limit you want to have as resolution, I mean the decimals on the panel of the scale, must be at least the same order as the standard deviation of your sample set. And in this particular measurement that we demonstrate here, that the standard deviation was 0.4 milligram. So that means a scale shall have at least 0.4 milligram resolution. But then we also have a rule of thumb. So that was the lower limit that we can accept. But we should try to aim for this rule of thumb, and that is that the resolution should be half the standard deviation. So if the standard deviation was 0.4 milligram, we should aim for 0.2 milligram. Then that will be ideal. But in our example here, we see that the scale already, that simpler scale already had 0.1 milligram. So that fits more than enough here. So it's twice as good at that rule of thumb of 0.2. So going to 0.01 milligram resolution or 0.001 milligram resolution, as we demonstrated in the earlier table, that is just wasting money here. It will not improve measurement uncertainty. So you need to get that idea here now. So continuation of how do I know if my instrument has enough resolution. So here we have changed the histogram now. So the previous histogram had, that's the standard deviation of 0.40 milligram. And that was actually data from coated copper coins, 100 coated copper coins. Used from electrode coated copper coins. So here now we only have the clean uncoated copper foil, and we know a copper foil is quite specular if you look on it, and it's smooth in the surface. So that signals that the variation in the spread of if you punch out 100 coins from that foil and measure them should be narrower, and indeed it is. So here we see that the standard deviation becomes 0.12 instead of 0.40 milligram. And we see in the histogram that it's measured with the same scale on the same scale with same resolution, 0.1 milligram, and it's about 6 boxes now that fits. And as I said, if it goes below 4, then you're starting to go over the lower than the acceptable limit that we demand in resolution. But here it seems fine. And if we're following the rule, as I said, if the resolution is the same as the standard deviation was 0.12 here, resolution 0.1. So that means it is a little bit better. So we are on the lower side, but still in acceptable range. So even for this case, 0.1 milligram resolution scale is good enough. And especially, I will say, since we're going to talk in this presentation about electrode coating, the coating weight will be the interesting part. And that will increase the standard deviation as we saw. Then if you're measuring in the clean copper foils like this will be perfectly fine. So this PPT is a self-help about normal distributed datasets. So we only work with normal distributed datasets. So what is a normal distributed dataset? So now I have on the slide the same old histogram with our coated copper coins that had that larger standard deviation of 0.40 milligram. And we can see that the bell shape actually follows those bars or boxes in the histogram pretty well. And that is the definition of a normal distribution set. It should look bell-shaped. The histogram shall look bell-shaped. And this PPT is only handling these kind of measurements. So here we have an example of a dataset that is not normally distributed. And we see it's still about the coated copper coins, right? But now we are having a different physical quantity. We're measuring thickness instead. We see there is thickness here on the x-axis, right? So if we look on the boxes here, they tend to aggregate in their own groups. They have some peaks at about 10 micrometer spacings and things like that. And it doesn't follow the black line at all, really, which is the bell-shaped curve. So this is a perfect example of a data set that is not normally distributed. And if your data look like that, then you need professional help, basically, because then you're in an advanced case. So then this PowerPoint will not help you on that. Okay, to help you understand this topic of measurement uncertainty, as I said initially, we will do scenarios that we have been taking from these performance battery tests of coin cells. So the idea is overall general, so you can learn from this even if you don't work with the battery measurements. But it is about comparison of two data sets. You have one set of reference data. We usually call that the before data set. And then we have one data set where we have done some modification. We call that the after modification data set. And now you want to prove, does your fancy modification giving any significant result, right? And that is a comparison of reference set and modified set we want to do. This is what we're going to learn in this presentation. So if you already is saying things like, if I say like this, that you measure a mean specific capacity of 300 milliampere per gram in your reference set, and then you're measuring 500 milliampere per gram in your modified set, and then you ask, is this a real significant result? I mean, it's obviously an improvement, 500 instead of 300. But if you say that you ask, is this a real significant result? That indicates that you understand part of the problem already, but you lack the knowledge how to calculate uncertainty and its propagation. So that is great news. You are halfway there. You have understand the idea behind it. But if you're in the more worst case scenario, so if you do something like that, you have made one cell, it showed 500 milliampere per gram. And then you look up in theory, so you haven't even done a reference measurement. And theory says it should be 300 milliampere per gram. And then you say that is an improvement, and you also calculate in percentage the improvement, and you get the number 66.66666667%. And you made sure to add all those digits in your calculation, because that shows how accurate your measurements really are, right? If you're in that case, then it is really bad, and you really need this presentation, and it must be mandatory reading for you and to study. The basics of statistics 1. Okay, you need to distinguish between two concepts. The first thing is things that refers to single samples. And what I mean by that, it can be, for example, a single measurement. You measure the mass of a coin. And the observed spread you see between different measurements like that we call the standard deviation sigma. So standard deviation is something that relates to single samples, so the domain of single samples. So this domain of single samples you need to distinguish from the domain of mean values and data sets. That we can call it the multi-sample domain or the mean value domain or something. So mean values obviously belong to this category. And standard error, SE in short, also belongs to this. So here you can see that standard deviation is a single sample thing. Standard error is a multi-sample thing. And you should never mix these two concepts within the same calculation. It's very important that you understand that. So either you live in the single data space and you do single data comparison, one cell versus another. Or you live in the multi-data set where you have mean values that you compare to mean values. So you should never mix single values with mean values and things like that. That is just wrong. So this is the deadly error 3 that we had initially, that I subtract the mean value of reference from my single sample to improve accuracy. That is a crossover mixture of these two concepts, and that is bad. You should not do that. The basics of statistics too. So here's an example of that deadly error 3. So let's take this example. 5 persons decide to lose weight. So instead of comparing their new weight with their own starting weight, they calculate the mean value of their initial weight that they have together in this group of 5. So the individual start weight, we can call that as B1, B2, B3 for these persons, and they are 80 kilo, 55 kilo, 122 kilo, 98 kilo, 65 kilo. And the mean value of those becomes 84 kilos, right? So after 3 months, they redo the measurements and measure their own weights, and then they get that the first person has not lose or gain anything. It still weighs 80 kilos. Second person has gained 3 kilos and weight 58 now. The third person, however, has lost a lot of kilos, 14 kilos actually. And the fourth person has increased 2 kilos. The fifth person has decreased by 1 kilo. So the mean value of this, the modified data set, as we call it, is now 82 kilos. So if we do, as we initially planned to do, that we subtract the reference mean, the initial mean value, from the single person's final value, then we can see we get for person 1 that one had a weight of 80 kilo in the end. So it has the same weight, right? But we're supposed to subtract the mean value of initial weight now, which was 84. That means person 1, according to this approach, lost 4 kilos. In reality, there was no difference, right? And the person number 3 that actually lost a lot of weight, the one that decreased most of the whole group, had a final weight of 108 kilo, and we subtract that mean initial value of 84 kilos, which makes that person to actually have gained 24 kilos. So all this is of course bullshit, right? We clearly see that we cannot work like this, right? But then you say, right, but Magnus, this is a stupid example. But of course, you need to do pair-to-pair comparison. Everybody knows this, right? And in this case, it's obvious we should do pair-to-pair comparison. Yes, I say, it's true. But how about if you can't do pair-to-pair comparison? What do you do then? And I bet you do the same bullshit as this silly example, but you aren't even aware of it. The basics of statistics 3. So here we have a real bullshit example of that, the deadly error number 3. And that is, you want to find out the electron mass of a coated copper foil coin. Ideally, you want to do pair-to-pair comparison. That means you would like to measure the weight of a single copper coin before you coat it, and then you coat that particular coin and measure the final weight of that coin. Then you can calculate the electrode mass by doing subtraction of after coating minus before coating, right? But here's the catch. You can't coat a single coin. The coin is just 16 millimeter disc that is punched out from the copper foil. So you cannot really coat that small coin in an accurate way. So this becomes an experimental limitation. So what are you going to do then? Well, you could take a whole foil, and then you measure the whole foil before you coat it, and then you coat that whole foil. That is how you do the coating. And then you punch out the coins. So what you're having in that case is, if you're measuring the weight of the whole foil, then you can calculate the mean value of the punched out coins that you will get. And you can also calculate the mean values of the punched out coated coins, right? And then you get the mean value of that electrode weight that you have on the coin. But you have no understanding of the standard errors of these mean values, because you only have one measurement of that mean value. You only put the whole foil once on the scale, right? And once after the coating on the scale. So here comes the bullshit thing again, right? You take the uncoated copper foil, you weight that, calculate the mean value of empty coins from that. And then you punch out the coated coins, and then you measure those coated coins individually. And then you calculate the coating weight of that individual coin by subtracting that mean value of the uncoated copper coin. So now you're doing that bullshit error again. You're mixing up single sample data with mean value data that belongs to the multi-sample domain. So then you say, but Magnus, what else can I really do here? Right? I mean, I must subtract some kind of, the reference must be subtracted to get the coating weight. Shall I just take a random uncoated coin? Is that what you want me to do? I mean, wouldn't the mean value be better in this aspect? I mean, I like mean values. I've heard mean values is more accurate, right? Well, then my Socratic question to you is, in the following case, what do we want to determine? A, the performance and its uncertainty of result of a single cell, or B, the performance and its uncertainty of result of the data set, actually the mean values. So if you're measuring the whole foil after and before coating and subtract those, then you get comparison of mean values, more or less. But you don't have any information about uncertainties at all. So that doesn't fulfill either A or B. If you do that, you're measuring single coated coins and subtract the mean value of the reference, then you are not in the A case either, because you have done this crossover bullshit. So actually the true answer here is, it is better to take a random coin that is uncoated and subtract that. Because if you have random uncoated coins, that means you also have information about statistics of those coins. You know something about the standard deviation of uncoated coins. And since you're measuring the coated coins also, you have information about the standard deviation of the coated coins as well. And that you can work on. The basics of statistics 4. So here we have this histogram of our uncoated copper foil coins again. The one with the narrower distribution. So let's go through some basic definition of statistics. When we write something in angular brackets, then we are referring to the mean value of that data set. If we're talking about sigma, then we mean the standard deviation of the samples. And the standard deviation is something that belongs to samples, and the standard error, in short SC, is something that is related to that multi-sample domain, or the mean value in this case. And there is a relationship between standard error and standard deviation, and that is that the standard error is the square root of numbers of samples smaller than the standard deviation. So if in this case, in this histogram, we had 100 measurements. So that is the reason why I say that the standard deviation is 10 times larger, because square root of 100 is 10. So if you take the standard error in this case, that was 0.012 milligram, it will be square root of 100 larger. That means 10 times larger. So it will be 0.12 milligram. The basics of statistics 5. So we have the same histogram graph of the uncoated coins, and the mean value here is 45.470 milligram. Its standard error is, as I said earlier, 0.012 milligram, and the standard deviation becomes 10 times larger, 0.12 milligram. And when we write numbers like this, then we are using something called 68% confidence interval. What I'm saying here is that if there is no more information than the number of standard error or the number of standard deviation, then we're having 68% confidence interval. So if you're not having 68% confidence interval, you need to tell the reader that you are in a different interval. And confidence interval means that if I repeat the measurement multiple sets over and over, 100 samples each, that means I take 100 samples, I measure them, and then I calculate the mean value and standard error. And then I redo it, take another batch of 100 samples, calculate standard error and mean value, and another batch of 100 samples, and so on and so forth. Then I will find that 68% of all these mean values will be found in this range of 45.470 milligram plus minus the standard error, which is 0.012 milligram. If we instead is talking about a confidence interval of 95%, we get that interval by multiplying the standard error by 2. So in this case, the standard error was 0.012, and then it becomes twice 0.024 milligram. And in standard practice is to use 95% confidence interval when you want to prove something, which is the main point of this presentation, right? But you should only use 95% confidence interval in your last calculation step, because otherwise, if you have many intermediate steps, it becomes a factor of 2 multiplied by a factor of 2, and that is the wrong way of doing it. It's only in the end you add 2 sigma confidence, as we say it, 95% confidence interval. So otherwise, if we don't mention that we have a 2 sigma confidence interval or something like that, then the reader defaults think we are in 68% version, and this was also referred to as the 1 sigma confidence interval. To all math stats people out there. And then now they will say, Magnus, hold your goddamn horses. And yes, what I said was not correct. I agree with you, math people. I should have said that if you repeat the experiment many times, each with n equals 100 samples, then approximately 68% of the calculated confidence interval will contain the true population mean. And also I should say that here a good approximation is to say that the mean of all these means will be rather close to the true population mean. But here's my point. This presentation is on the very low basic level to make it pedagogically accessible for the viewers to grasp the main idea behind these things. And these main ideas is, for example, to distinguish between sample and sets. And another less good approximation that we will use here is to say that the mean value of one set is close to the true population mean. And if doing so, the previous statement holds. So we will also say for the same reason that 95% confidence interval is achieved by multiplying by 2. In reality, it should be 1.96 that we multiply with. We will also believe that 4 sigma will cover 100% of the data. And that's the reason in the previous example I said that the standard error of 0.012 at 68% confidence interval just becomes twice 0.24 milligram at 95% confidence interval. And it's the same thing. We will not distinguish between the true value and the mean value of the data set. So that's beyond the scope of this presentation. And math people, they told me once that there is both real and irrational spaces. And since we talk about real measurements here, and math people don't really do measurements, right? Then which space these complex types belongs to kinds of narrow it down, don't you think? The basics of statistics 6. So here we have this same histogram with that uncoated copper coins with that narrow distribution. Mean value was 45.470 milligrams. Standard error still 0.012 milligram, right? So what this means is that if you take a random coin from this set and then you measure its mass, then the spread of values you get, if you repeat it, you take another coin, and you look on that table you create, how much does the number fluctuate, the spread. That is given by standard deviation. It's not the standard error, the standard deviation. And the standard deviation is 10 times larger than the standard error in this case, because we have 100 samples. Square root of n, you know. And this is very important for you to understand, because if you do capacity performance measurement of a battery coin cell, it will depend on electrode mass. And electrode mass is something you have on each single cell. That means the fluctuation in capacity that you will see, the spread in capacity, will be directly proportional to the spread in electrode mass, right? And since the spread in electrode mass is caused by the standard deviation, it will be 10 times larger if you're measuring 100 cells than this variation in the mean value, right? And because of this, it is quite plausible that if you do calculations of electrode weights, for example, and you do that by measuring the mass of the coated coin and subtract the uncoated coin, right? Then that difference for single sample comparison can turn out negative. And then it actually looks like that when you coat the copper, you're supposed to add the electron mass, right? How can it become negative? How can it be less mass than the initial copper foil? So this is a statistical phenomenon that happens when the distribution of the two data sets starts to overlap. And the more they overlap, the more these kind of negative weird values you will start to see. The basics of statistics 7. So let's repeat the last statement. If one measures one coin cell's performance, then another one, the spread of all these individual cells' performances will be governed by the standard deviation sigma, and hence It is 10 times larger than the standard error of the mean performances if you have 100 samples in your sets. So this brings us to the error 4, the deadly error 4 on the initial slide, where I said, yes, I only measured one sample pair, and if my data after minus data becomes larger than 0, then this proves my point, my thesis. And if it's not larger, then I just redo it, because then it was probably caused by measurement error or equipment or me. So here you see the thing. The standard deviation makes the fluctuations much larger when you do cell-to-cell comparison. And sometimes it turns out negative for you. And then you believe that is a measurement error somehow. But it's not. This is caused by statistics. So if you do that kind of calculations, what actually going on here is that those that is negative values, you don't just put those aside, and you don't count them as real data. There's something flawed in them. That's what you think. And the one that actually shows some performance, those you keep. And then you say that here you see how they increase, right? And if you are in this case, you have proven nothing. Because even if you see an increase in a few coins or many coins, you cannot say you have proven anything if you don't bring along the measurement uncertainty into the equation. And when these kind of ways are being done, reviewers will call that cherry picking. And that is a typical student failure in the first hand, and in short, it is called a fraud. The basics of statistics 8, calculation example. So let's use the previous data where we had this 100 coins data sets of each, before and after coating. So the uncoated copper coins mean value, that is the B before set as we call it, has the mean value of 45.470 milligram, and the standard error was 0.012 milligram. Then we have the coated copper coin version, the A set, that means after modification, coating in this case. Mean value 46.003 milligram, standard error 0.040 milligram. So if we have that, and then we just take out 5 random coins of each, and then we make this table. Then we see in the table that the first coin in after the coating has mass 46.3, second coin 46.5, and then we have 45.8, 46.4, 45.7. And before the coating we have 45.5, 45.8, 45.5, 45.3, and 46.0. So overall, it looks like there is smaller numbers in the before set and slightly larger numbers in the after set, right? And if we just do the calculations and subtract the before data set, the uncoated coin weight, from the coated weight, right? So let's do that, and we can look. If we take the first row, 46.3 minus 45.5, that becomes a positive value. So that tends to show us that we have actually some kind of coating weight. But on the last example, 5 here, we see that after coating, mass is 45.7, but before it is 46.0. It's important you understand it's not pair-to-pair comparison here. These are they are random sets that we put against each other, right? So that means for that 5th row comparison, we get a negative mass of minus 0.3 milligram. And this is the thing that I tried to explain to you, that you must understand that this spread in single sample comparisons is so large. So due to natural variation in the materials of the copper foil and the coating weight is what give rise to these weird results of negative values and so on. It is not caused by using scales with too low resolution or that you're doing the measurement in a poorly way and so on. the basics of statistics 8. Aim of this PowerPoint presentation. So, that is to learn to calculate these standard deviations, or what shall I say, the combined standard deviations that you get when you do a minus B comparison test of single samples, and also to calculate standard error from comparisons test of mean values. You're going to learn to calculate these error propagations, and here we see, I can give you the number that the standard deviation will be 0.42 in this particular example when we do cell-to-cell comparison. And the corresponding, when we do mean value comparison, it will be 0.042. So mean value in this case is having a combined standard error that is 10 times less than the combined standard deviation, right? And we're also going to learn in this PPT that we need to understand that we need to use 95% confidence interval when we want to prove these kind of comparisons is larger than 0, as we say in layman terms. And the last thing we're going to learn is that depending on what the maximum uncertainty is, this will allow you how much the improvement actually must be to be able to say it is statistically significant. So proving if the improvement that you have shown is only 5%, the demand to having low measurement uncertainties become very demanding. But if you're measuring an improvement of 50%, then the demand of measurement uncertainty being low becomes less problematic. So let's just do the calculations here in our previous example. So if we calculate the differences of mean values of these 100 coins coated set minus 100 coins of the uncoated set, we get that the difference, the coating weight that is, becomes 0.533 milligram, right? So if we calculate how much relative increase is that compared to the weight of the full coin, then we see it's only 1.2% heavier. So it's a very tiny increase actually. So what about the combined standard error here now? The combined standard error in this case must be on average better than 0.19 milligram. And in this particular example, we had 0.4 milligram and 0.04 and 0.012 milligram. So we are way below the threshold. So this is indeed a significant result that we're having here. But if we do the same calculation, but by instead doing single cell comparisons, then the standard deviations that we have to use is of course 10 times larger than the standard error. So then we are in 0.40 and 0.12 milligram case. And this becomes now larger than that 0.19 on average that is the demand in this particular example. And hence it is not statistically significant any longer to do cell-to-cell comparison. The distributions overlap too much, and that is the reason why we see negative values sometimes. The basics of statistics 9. So let's revise the deadly error 3. And you remember it was this thing that, yes, I subtract the mean value from my reference from my single sample test to improve accuracy. And we understand earlier that this is the issue here is we're mixing concepts from single samples that we're measuring with multi-sample data sets like mean values. And the problem here is that the calculating the errors becomes impossible. There is no such thing that you can use both standard deviation and standard errors in the same formula, right? So, I mean, what would it mean, right? So if we calculate the combined standard deviation of a single sample comparison, it becomes 0.42. If we had a full mean value comparison, mean value after coating, mean value before coating, Then we use the standard error with this 0.042 milligram instead. So what would it, some kind of hypothetical combined error, if we're doing the single sample minus the mean value, what would that error sort of represent? It doesn't have any scientific meaning. But if we anyway do such a weird calculation, let's see what will happen. So if we do that, then we will get a number that will be 0.40 milligram. And then that we can compare to the standard deviation of single cell comparisons, which was 10 times higher, 0.42 milligram, as we talked earlier. So if the idea was to improve accuracy, we see that we don't really do that. 40 is almost the same as 42, right? So what's the point? So it is true in some way that you get a better representative value of the substrate by using some kind of mean. But in this context, the important thing here is that to bring along the uncertainty of single samples, that means the standard deviation, by measuring it into your performance calculations of the device, and to not use standard errors if you're working on single samples. The basics of statistics 10, a significant result. So here we see two histograms. The top one is normally distributed, bell-shaped curve, and it has a mean value of 46.003 milligram and standard error of 0.037 milligram. The second data set below here, also normally distributed, but the arrows here marks out the mean values, and we see that the second set is a slightly offset in mean value. The mean value for the second set is 46.114 milligram. Standard error is 0.039 milligram. So that means that the shift is 0.111 milligram, 0.111 milligram, higher than the first set. Is that difference significant, we ask? So we do our standard comparison test. The separation must be larger at 95% confidence interval. That means we multiply the combined standard error by 2. And the combined standard error we calculate as the square root of the quadratic sums of the individual standard errors. So all this calculation ends up till that the separation must be larger than 0.110 milligram. And it was 111. So this is a statistically significant result with 95% confidence interval. The basics of statistics 11. A significant result is hereby defined as that the separation of the mean must be larger than 2 times the square root Pythagoras sum of the individual standard errors, and that was 0.11 milligram. And this is what you get when you're working on mean values of set of 100 samples. 0.11 milligram relative to mean mass is just 0.2% in this example. So that is very good accuracy, right? So what about if you instead do a single cell comparison on this data set? Well, since we have the set of n equals 100, the standard deviation, sigma then, relates to the standard error, as we said earlier, that it will be square root of the number of samples larger, hence 10 times larger. So let's do the same calculation then with standard deviation. So instead, we get the sample test significant threshold on single samples, the A minus B test, must be larger. If we do the same calculation, multiply by 2 for 95% confidence interval, and then the Pythagoras sum of those individual standard deviations. And then we end up that sum becomes also 10 times larger than before, 1.1 milligram instead of 0.110. 110. So that is the same as it's 2% relative to the mean mass instead of 0.2%. And we see a mass difference between a coin measured from set B and a coin from set A. We can say that for a single coin test to be significant with 95% confidence, then the A sample's mass must be at least 1.1 milligram higher than B. So all tests that shows lower masses is therefore not significant. So in these two sets that we had, for example, we cannot find any single cell comparisons that actually will be significant. Well, yeah, a few. We showed that earlier, but most of them will not be higher than 1.1. The basics of statistics 12. Value of a single measurement. So here below I have 5 random samples taken from these 2 earlier data sets of n equals 100. So set A after is our coated coin set. After the coating, that is. That's what we have here in the first column, 5 coins. Set B is before, you see there. And if we do the calculation of the differences, so we take the after weight minus the before weight from these random coins, so it's not pair-to-pair comparison directly, right? Then we see we get negative values. 46.3 for the coated coin minus 45.5 becomes minus 0.8 milligram in difference. And so on. So as we see, no one of these 5 rows actually has a difference about 1.1 milligram. In fact, almost all is negative values, except the last one then, 46.0 milligram coated versus 46.0 milligram uncoated. So that actually gets just 0 in difference. So this, in a first glance, as I have said earlier, makes it looks weird. How can we have like negative mass differences after we coat the sample? And that is because that the negative values is a sign that is observed when the distribution starts to overlap. And the message here is that you must understand that this is not a measurement error and you should stay away from cherry picking. And by that I mean you're disqualifying these negative results and saying that must be caused by the measurement instrument or something. It is not. It is caused by statistics because the observed when distribution starts to overlap. So if I go through all the 100 coins and looks on the data, do we actually have anyone that will be significant? And in fact, we can find that out of these 100 samples, there will be 5 outliers that actually has a mass difference about 1.1 milligram. So at 95% of all samples individually measured will not be significant. The other ones are the significant outliers we see, and I have put them here in the table below. So here we see the 5 coins that actually become significant if we do the subtraction. And the differences in mass, the coating weight that is, will be 1.9 milligram, 1.2 milligram, 1.2 milligram, 1.2 milligram, and the last one 2 milligram. So this is very important you understand how we can see that mean values reduces the uncertainties, and if the mean value is based on sets with large number of samples, we get very high precision in that. But if we go back to single cell measurements, that standard deviations become large, 10 times larger in this case, which give rise to these negative numbers. The basics of statistics 13, working on mean values. Since our coated coins are related to the uncoated coins, but we can't measure the uncoated weight before the coating starts, so to say. We talked about that earlier. That was the limitation that gave rise to this deadly error 3. So single cell comparison becomes weird overall. What reference mass shall we then subtract in such a case? Shall we use a random number or the mean value as we discussed earlier? So here's the thing. You shall only use mean values together, and you should try to stay in that domain. Never mix them up. But it is still useful to have some kind of awareness of the single cell performance. Hence, it is this aspect wise to estimate the performance range of the single cell from the uncertainty range given by the standard deviation instead of the standard errors. Otherwise, you shall stay in the mean value of sets domain. So, if we have that n equals 100 samples in the set, we also know on the fly that the variation between individual cells will be a spread that is 10 times larger than the variation in the mean. The reverse is not true, because if you measure, as I said, that you're measuring the whole foil mass before coating and the whole foil mass with the coating, then you calculate the mean value of the coated coin and mean value of the uncoated coin. The mean values will be correctly determined in some way. However, you will lose the uncertainty that's caused by the punching itself. But besides that, it is fine so far. But you only have the mean values. You have no understanding about the standard deviation of the single samples, or the standard error of the mean, by the way. So that's the problem, right? The reverse will not be true. So if you do 100 samples and measure them and get the mean values, then you also get the standard error on the fly. And then in turn, you also know something about the standard deviation on the fly. So the only way forward is to work on mean values from set. That is the recommended way. So then comes the question, how many samples shall I then run in a set? I mean, n equals 100 is a lot, especially if it comes to like galvanostatic cycling of cells. I mean, cycling a cell can take months. And are you supposed to have 100 separate channels on the potentiostat? Well, theoretically, n equals 100 is like the lower limit from a statistics perspective. And yes, I agree, it is insane. So practically, in this testing the capacity of coin cells, 5 is like the acceptable numbers that you can manage in this case, from a practical perspective. And this is because since you also want to do before and after, that means 5 coins for a before measurement test, 5 coins for after measurement test, then you suddenly have 10 coins to test, and most likely you want to have different types of modification as well. So these 5 coins tend to multiply anyway to a big bunch of coins. So here's the catch. If we're going to stay on 5, we will be punished by this lower number of samples. And this we must be take into account and compensate for statistically. And this thing we can do, and we call that the student's T correction, or the expanded uncertainty. And the basics of statistics 14, student's T correction. So, to compensate for that low number of samples, we multiply our previous calculated standard deviation with the T factors, as it is called, from the table below. This we call the expanded uncertainty. And at this basic level, we can just forget about the degree of freedom that we see here in the table and only look on the number of samples and what correction factor we should use. We see there is one column for 68% confidence interval with correction numbers. If you're running 5 samples, we see that that correction will be 1.14. Hence, we compensate by adding 14%. And we also have a 95% confidence interval here. So with the same 5 samples, that correction factor will be 2.87. So let's do this calculation on a subset of 5 samples from our previous 2 sets. So we pick out 5 samples from the uncoated and 5 samples from the coated. That means the A set is after coating, B set is before coating. So here we have them. After coating, 46.3, 46.0, 46.3, 46.6, 46.0. milligram, all of them. Before coating, 45.5, 45.9, 46.0, 45.8, 46.0. That's before coating milligram. We do the calculation. The standard error for the before coating set becomes 0.093 milligram. And for the A set becomes 0.11 milligram. The standard deviation we can also calculate, so sigma for the B set becomes 0.21 milligram, and for the after set A set it becomes 0.25 milligram. And look, now you see it's not 10 times larger, because it's supposed to be square root of the number of samples, and in this case we only have 5 samples, so it becomes 2.2 times larger this time. So with the student T correction, we can go up in the table. We see for 5 samples, we should do the 1.14. That is the factor we should multiply it. That is the student T correction. So if we do that, we get the total answer of the before set's mean value become 45.84, and the corrected standard error becomes 0.11 milligram. And that is instead of this 0.093. And for the A set, we get the mean value 46.11 with the standard error of 0.13 milligram instead of 0.11 milligram. And we can do the same thing with the standard deviation also. That should be the square root of 5 larger. So for the B set, we get sigma B becomes 0.24 milligram. And sigma A becomes 0.29 milligram. The basics of statistics 15, students T correction continuing. So with the students T correction at 68% confidence interval, we get that the factor to multiply with was 1.14. So we increase the standard error by 14%. So, and then we get for the B set 0.11 milligram in standard error. And the standard deviation became 0.24 milligram. So let's just look on the B set now. And then we compare our 5 sets, standard error and standard deviation, to the original 100 coin set result. In that case, the standard error was 0.037. But in our corrected 5 set, it was 0.11 milligram. So it is a little bit larger, you see, in our 5 coin set. N equals 100 sample, we see that we have 0.37 milligram in N equals 100 coin set. But in the 5 sample coin set, the standard deviation was 0.24 milligram. So what's going on there? You see that the standard error was larger in the 5 coin set compared to the 100 coin set. But the standard deviation was smaller in the 5 coin set compared to the 100 coin set. And the reason for this is that the relationship between standard error and standard deviation depends on the square root of number of samples, and those are different between the sets. Hence why we get these differences when we compare standard deviations and standard errors. So all this is on 68% confidence interval, and you should remember that this is the confidence interval you shall normally use in all intermediate steps of calculation. So it's only in the last step of comparison that we switch to 95. But we can see here what happens if we increase the confidence interval in the student T correction. So let's go up to 95 just temporarily. Then we see that the correction factor becomes 2.87. Right? So now the standard error in the 5 coin set becomes 0.27 milligram. And in the original N equals 100 case, then you remember perhaps to get 95% confidence interval, we do the 2 sigma thing. That means we multiply the standard error by 2. Then we get 0.74 milligram. So in this case, 5 coin set had 0.27 and the 100 coin set became 0.74. That's a little bit more than twice. So this seems to come a little bit closer. And in the standard deviation, we see that in the 5 coin case, we had 0.6 milligram. And in the 100 coin case, we have 0.74 milligram now. They are almost about the same. And then we can do also a 99% confidence interval. I didn't put that numbers in the student T table, but they actually exist those tables as well. And here the correction factor will be 6.62. And if we just look on the change in standard deviation now, we see for the n equals 5 case, now the standard deviation is 1.4 milligram, but in the 100 sample case, then we should multiply by 3 this time, we get 1.1 milligram. So now the standard deviation has become larger for the 5 coin side. So the higher confidence interval we choose, the more and more we are punished by increased standard deviation in the correction factor from the student T correction. It's good to remember that. And we can look also on the correction factor itself. I mean, theoretically, in this n equals 100 set, we have 1 sigma. That sort of corresponds to a student T correction that is 1.0. But for 5 samples, we see 1 becomes 1.14. So that is a small increase, 14% increase in that uncertainty of the standard deviation. When we go up 95%, then in the 100 coin set, we multiply by 2. But now we see that the correction factor is not 14% higher. It is 2.87. And if we compare that to 2, we can see that that is more than 14% increase. That is almost 50% increase. And if we do the 99%, then we see that the T correction factor is 6.62 compared to 3. So then we are more than twice punished by that correction factor. And the basics of statistics 16, variability between sets. So now you must understand that if we repeat our 5 samples into multiple sets, then we get the table below. And for each of these sets, the standard errors in the brackets has been student T corrected. So what we're having here is that from the main set of the after coating, those 100 coins, I have picked out 5 coins, calculated the mean value of those, calculated the standard error of that mean, and corrected that with the student T correction. And I've done that 5 times. So we get 5 mean values. That is what we have in the table here. And I've done that the same for before the coating as well. And since all these 5 comes from the same main set, the after set, and all these other 5 comes from that before set, technically they should be the same, right? It's the same main set underneath. But we see there is differences. I mean, these mean values are different from each other, and also the standard errors changes. And that is the reason why we talk about the true mean of the set, and that our approximate measurements of this mean by single sets with limited number of samples. And the change in the standard error we see also is interesting, because if we have a significant change in the standard error, that means that there will be a change in the material itself. It has become more rough in some way, it's causing more variance and spread in the coins. So how do we know if these sets are the same? Obviously the numbers are different. This question is the same thing as asking if they are different. Right? Do you understand that? If we cannot prove they are different, then the thing that remains is that they must belong to the same set. Or actually, we cannot tell they are different, so they could be the same. That's the correct answer. So we can do the same comparison test. We compare the mean values, and then with 95% confidence interval, we get that by multiplying the combined standard error, that Pythagoras thing, by 2. So if we take the first two mean values from the A set here we have mean value 45.84, standard error 0.11 milligram. Second one had mean value 46.32 with standard error 0.17 milligram. 0.17 squared plus 0.11 squared, and the square root of that times 2 becomes 0.40 milligram. And the difference, 46.32 milligram minus 45.84 milligram, becomes 0.48 milligram. So, at this 95% confidence interval, A1 and A2 are not subsets because the difference is larger than that sum we calculated of 0.40 milligram. The difference was 0.48. So here, since we know that they come from exactly the same set, this is the statistical outlier, those 5% that we saw earlier. And if we do, we can get the opposite result as well. So if we compare the second set, 46.32 milligram with standard error 0.17 milligram, with the third set, 46.08, standard error 0.33 milligram, then we see that the differences is minus 0.24 milligram. But we only look on the absolute values. And this difference should be larger than the 0.74 milligram, which is that combined standard error times 2. And it is not. These two are not significantly different. And here is when the students become scared. Because they say, well, Magnus, when we're doing this test, isn't it the test supposed to test if it is significant or not? And here we see that 5% of the times when we do the test is faulty. Because in this example you showed, we know that all these subsets came from the same main set. So if it says it is significant, that is like a false outcome of the test, right? Yeah, and that is the point, because it's 95% confidence interval. So you can see that as the test itself has 95% accuracy of being valid. So if you really want to have 100% for sure, true or false, that's when this 4 sigma comes in. So instead of multiplying by 2, we multiply by 4. Then we consider that to be 100% for sure, so to say. But for sigma test, it's not what we consider to be the default policy. So we should do the 95% test. That is the normal. And you just have to live with the thing that the world is not 100% anymore. The basics of statistics 17, error propagation formulas. So from where does these previous calculations derive from? When I say that we calculate the combined standard errors via this Pythagoras looking square root thing. We already know that the factor of 2 comes from that 95% confidence interval. But the square root thing, what's that? That comes from that thing that we call error propagation. And the uncertainties are added in this geometrical way to give some kind of statistical, what shall I say, fairness. I mean, if I say like this, it is unlikely that all errors work together in the same direction to make the worst possible case for you. More likely, you can add them, as we tend to say, 90 degrees separated. That's the reason why it becomes this Pythagoras thing. So, and here's the first point to learn. If we doing calculations to find the combined standard error for a calculation that is based on addition or subtraction. Like we're comparing differences, take A minus B. Those kind of things. The standard errors are added by their absolute numbers. So we take the standard error of the first set in square plus the standard error of the second set in square and takes the square root of that sum. That is the combined standard error when there is addition and subtraction involved in the calculation. So that means the absolute value of the standard error is important, that is low. Then we have higher possibility to prove that our difference is significant, right? If we repeat what we did earlier, then we had the reference uncoated coin sets, the B set, the before set's mean value was 45.470 milligram with standard error 0.012 milligram. The coated coin's mean value, the A set, was 46.003 milligram, standard error 0.040 milligram. So, if we do, since this is, we want to do a subtraction comparison here, A minus B, the mean value of A minus mean value of B, that should be larger than 2 times the sum of that propagated standard error. So we do the Pythagoras thing. The standard error of the first set was 0.012, take that in square, plus the standard error of the second set, 0.040 in square, sum them together and takes the square root of that. Then we get 0.042 milligram. So the coating weight we can present as being 46.003 milligram minus the other mean value, 45.470 milligram, which gives you the difference, 0.0533 milligram. And then we write that the standard error of that calculated difference becomes that 0.042 milligram. And in our short version of writing this, we write 0.533 bracket 42. And all this is 68% confidence interval, because we haven't said anything about confidence interval. So that is the default, right? So if we want to say if this difference is significant, then we multiply this combined propagated standard uncertainty by a factor of 2 to get that 95% confidence in. So that's the policy. So the lower boundary, 0.533 milligram, that is the mean value coating weight, minus 2 times the standard error. The standard error is 2 times 0.042 milligram. That means that the lowest value is 0.449 milligram. And that is a larger number than 0, right? Hence, this is a significant coating weight that we have calculated here. But remember that for comparison of 2 single samples instead, propagation will be based on standard deviations instead. And those are of course larger, and in this particular case they will add up to 0.84 milligram. So if we do a A minus B test of single samples, then this will not result in a statistically significant result. So comparison of single coin cells of these A and B sets, they are too close to do any significant proof of a single coin subtraction. The basics of statistics 18, the issue with subtraction now. So let's look deeper into this. So the error propagation is, as said, is when we do addition or subtraction calculation, that we add up absolute numbers, not relatively. So that the combined standard errors is the sum of the squares of the individual standard errors. And this makes a concern for us, because the active mass of your electrode of your coin, you do a subtraction. So then you end up with this kind of error propagation. So what contributes in such a case to a large standard error? So here you must understand there's two things. It is both the smoothness of the foil or the coating, and it's also the weight of the same, since it is absolute numbers that we're adding. So a small variation in a very heavy coating, solid coating, or actually if we take the metal foil is solid metal. That's very heavy, very high density. So even if the copper foil is very smooth, I mean it's specular on its surface, that small variation in surface will still give us a large number since the foil itself is heavy. A coating, on the other hand, is much lower density than the metal foil, but the roughness is much higher. So to get a low standard error, both must be small. But here is also a catch, that we want the coating mass to be high, because that is something we need in the experiment. So when we say that we want to have low mass, in this case that will result to that it is the mass of the copper foil we want to keep as low as possible compared to the mass of the coating. That is important in this aspect. The basics of statistics 19. So here is the issue with multiplication then. So if we do error propagation, I mean, we have already talked about addition and subtraction, but we also have the case where we do multiplication or division. If you have that scenario, then we don't add the absolute numbers of standard errors. It turns out that we add the relative standard errors. And by that I mean we take the standard error of the measured mass, for example, the mass of the uncoated coin, and divide that by the mass, the mean mass of the coin. So that percentage, that is the relative uncertainty that we're having. So if we do the calculation on our previous sample, we saw that the coating weight became 0.0533 milligram with a standard error of 0.042 milligram. So how big is that error relatively? So we take 0.42 milligram divide by 0.533 milligram, then we get 9.7%. So here comes the thing. What equation down the line uses multiplication or division instead of addition and subtraction? And that we have because we are measuring the thing called specific capacity, CS. So if we want to decide what the specific capacity is, that is, specific means that we normalize against mass. We divide by mass of the active electrode mass of the cell. So in the potentiostat, we are measuring the absolute capacity. And then we divide by the mass of that electrode. Then we get the specific capacity. And how the potentiostat measures that capacity, that absolute capacity, we use galvanostatic cycling, for example. And that by definition means in a potentiostat, static means that the current is kept static, galvanostatic, hence the name. So that is a constant in this case, and then we're measuring the time it takes to charge up the cell to a certain voltage. And from that we can calculate the capacity. So capacity becomes current times time. So then we can do a calculation of the mean value of the specific capacitance of our 5 coin sets, for example, by measuring the mean value of capacity and divide by the mean value of the coating weight. And remember, we divide by the mean value. We don't split it up and do that weird error tree thing where we take the individual measured capacity value and divide by the individual mass of that coated coin mass and subtract some mean value of the uncoated coin. No, we don't do that thing. Always work with mean values. So if we look on the standard error propagation for this scenario where we have multiplication, we clearly see that the errors is added relatively under the square root sign. So we still add them by this Pythagoras thing, but we add the errors relatively. So here we will have the relative error in the coating weight in square plus the relative error of the time measurement in square. But remember that I said that we in electronics usually have very good machines nowadays. 3% error, I mean, for that potential that to measure time, that is completely negligible, that error. So here, mass error in the coating weight will be completely dominant. So since we earlier calculate that to be 9.7, that whole square root of propagated error will be 9.7%. So times the mean value of the specific capacity. So this is important to understand and see the distinctions here, that the errors tends to, or the uncertainties I shall say, tends to strike down on us in different ways, depending on if we are doing calculations based on additions and subtraction, then the errors comes in absolute numbers. If we're doing multiplication and divisions in our equations, then the errors strike us down by the relative values. Those becomes important now. 2 questions to ask yourself before continuing with your experiments. So now you can choose the route of planning an experiment by looking on the following 2 questions. Question 1. How much must the performance boost of my modification, these modified cells, have to be significant? That is the first question. This question becomes relevant when you already have prepared cells and wondering if your results are good enough to be statistically significant. I mean, do you see in your measurement they perform 10% better? The question is that good enough to be significant, or do you actually need to show that it must be 20% better? Question 2. How much coating weight do my electrodes need to have to statistically be significant to prove a X% increase in performance? So here we have sort of changed the theme on the question. This question is important if you're planning the experiment and you already know something about the expected performance outcomes, right? So if you know that these materials you're working on is expected, perhaps from theoretical calculations, that the performance increase should be 10%. Then the question becomes valid here. So how thick coating do you have to give you that kind of low uncertainty in your measurement to be able to say statistically those 10% you see in the data is actually true? Here's one more thing I want to emphasize. I mean, we talk a lot about coating weight in this presentation. And why do we do that? I mean, of course there are other uncertainties involved. But here's the key, right? Coating weight is the single most influential physical quantity that has been observed in lab work. And coating weight is the physical quantity that is normally controlled by you as a PhD student. And when you do the subtraction of that substrate mass, its calculations, as shown within this PPT, give rise to a large uncertainty by default that must be accounted for. So there are other errors, of course, involved in this. But if you can sort of grasp this idea and address this issue, because this is the largest uncertainty in your measurement, so you need to put focus on this. So this is the full before-after test how-to. So now we're going to go through step by step to do a full comparison test of coin cells before and after some modification, and to see if it is significant at all. So imagine the following scenario then, where you have done a 5 coin cell set of uncoated weights with standard errors. We call that the B set, of course, as before. And then we have 5 coin cells that we have measured with the substrate, the copper foil. And here that becomes 45.84 milligram with standard error 0.11 milligram. And then you make another set of coins that comes from a coated session. So you have coated the foil, pick out 5 coins. We call those B-coated. So the mean value of the B-coated set becomes 46.11 milligram. Standard error 0.13 milligram. And we do the calculation of the coating weight for that batch. Means we subtract the mean values. So we take the mean value of the coated mass minus the mean value of the substrate mass. 46.11 milligram minus 45.84 milligram. And then we get 0.27 milligram as coating weight. And then the standard error for that calculation, the combined standard error becomes 0.17 milligram. So how did we calculate standard error? Yeah, we just went through that earlier, but here it is again. It is the square root sum of those individual standard errors in absolute numbers, since we're doing a subtraction. 0.11 in squared plus 0.13 in squared. That sum we take the square root of, and we get 0.17 milligram. So step 1 in this full comparison guide is we need to check, is the coating weight significant to start with? So let's do this at our test we have practiced. This means that the difference must be larger. The difference is the coating weight, right? That was 0.27 milligram. That must be larger than 2 times that combined standard error. And 2 times 0.17 milligram is 0.34 milligram. And that is not larger than 0.27. So this coating weight we have made in this here, we can't continue this experiment. It is too little to be statistically significant. So we have 2 options. Either we can increase the number of cells in the experiment, then we will reduce the size of that combined standard error, and then it will be statistically significant after a while. But that is very tedious. We don't want to increase coin levels here. We want to keep the number of coins as small as possible from potential stat perspective. So then we only can do B, and that is increase the coating weight by redoing the coatings. So that's it, a hard truth fact here. And what is 0.27 milligram in coating weight? Well, we use a 16 millimeter diameter coins here, so that equals to 1.4 grams per square meter in coating weight. So that's too little for a 5-cell test, so to say. So if we assume that the standard errors don't increase with increased coating weight, then we can calculate what is the coating weight we actually need to be significant. And if 2 sigma is 0.34 milligram, that is. And if we do that calculations, we find out that we need at least 1.7 grams per square meter instead of 1.4. The full before-after test, so step 2. And here, initial measurements of coating weight, the B set before. So let's start over again now, since we had too little coating on the material. So let's do it the proper way now. We take a standard coating weight that we usually find on electrodes, that is 10 grams per square meter. So let's generate that. We still have our substrate set, the clean copper coins, 45.84 milligram with standard error 0.11 milligram. We use the same numbers as before. And then we have a new 5 coated coin set. The B coated mean value becomes 47.84 in this case milligram. Standard error 0.15 milligram. This corresponds to 10 gram per square meter. So let's calculate that. So we do the same calculation as before for coating weight. The mean value of the coated coins mass minus the mean value of the copper substrate coins, 47.84 milligram minus 45.84 milligram, becomes exactly 2.00 milligram. And the standard error is 0.20 milligram. And we see that it comes from the same formula of combined standard error calculation, that Pythagoras thing where we add this individual standard errors in square and take the square root of that. So that becomes 0.20 milligram. And yes, no, this is significant because 2 milligrams is much larger than 2 times sigma, which is 0.2 milligram. So 2 is larger than 0.4, right? So this is statistically significant coating at 95% confidence interval, right? So far, so good now. So now comes the new part. We don't just want to make coatings on coins that are statistically significant. Now we want to add the new part where we have another set of coins that has been modified. The A set, so to say, where we do some manipulation of that electrode material and see, does my new electrode material actually have some improvement? That's the fancy part, right? And here, from my experimental best practice, when it comes to these references, the copper substrate, right? We have measured 5 dummy coins, uncoated coins, in our B set, the B substrate. When I now do modifications of the coated coins with a new electrode slurry, why can't I just reuse that number? I mean, shall I take 5 new uncoated coins? And the answer to that is yes. And that is because that is the best practice. Always take a new batch, even if it's the same sort of uncoated coins. Because if you do that, and you should measure it on the same day as in the same situation. Because now we're working with copper foils, and that is very inert. So in this case, we will not see so much difference. But if you're working with more advanced materials or paper substrate and things like that, humidity in the room and room temperature and things like that will create uncertainties, right? So experimental experience is, as we said initially in this presentation, always good to have. The full before-after test how to. Step 3. The initial measurements of the coating weights of the A set, that is the set after we've done some modification of the electrode material that we want to prove is giving some kind of boost. So before we have already done the B set, and we came to the conclusion that the mean value of the coating weight of the B set became 2.00 milligram with a standard error of 0.20 milligram, 10% error. This corresponded to 10 grams per square meter in coating weight. So now the new part, we want to add the A set, where we do that modification of the electrode material, right? So that means we have another batch of 5 coin cells, both of uncoated coins and another 5 set with that modified electrode coating on. So in an analog way to the B set, we have our uncoated coins, the A subs mean value becomes 45.65 milligram with standard error 0.10. So there is a slight difference, of course, because there's always some variation. And as I said earlier, best practice is to make another batch of 5 uncoated coins to add into this set. Don't reuse the data from here. And then we have the coated coins set of with that modified electrode material. We see we get a little bit different weight here, a little bit lower. Instead of 47.84, it drops to 47.11 milligram, and the standard error is 0.22. So it's a little bit larger also compared to 0.15. We calculate the coating weight by subtracting the mean values of the coated electrode coins versus minus the mean values of the copper substrate. 47.11 milligram minus 45.65 milligram ends up to be 1.36 milligram per coin in mean value with a standard error of 0.24 milligram. And this corresponds to a coating weight of 6.8 grams per square meter. So, why does it drop? Why do I have that as an example here in our scenario? And this is quite natural thing, right? You do some modification. Let's pretend that this is a furnace treatment process or something like that. And then during that furnace heat up phase, you might lose material from the electrode surface overall, which means that the coating weight might become a little bit less if you do everything else the same. So, and also that the variance, the standard error increases to 24 compared to 20 here, can be caused by the same means. I mean, added porosity and things like that in the material, right? So, is this new set statistically significant in coating weight? We do the same test. That means the difference, the coating weight, 1.36 milligram, must be larger than twice the standard error, which was 0.24. So, twice that becomes 0.48, right? So, obviously 1.36 is larger than 0.48, so that with 95% confidence interval, we can say that this is statistically significant coating. And then we can proceed with our before-after test. The full before-after test, how to step 4. Now it's time to do galvanostatic measurement of both sets A and B. So, to summarize, before we have already calculated the coating weights of the before and after we modified the electrode material. So the mean value before modification was that the coating weight was 2.00 milligram in mean value with standard error of 0.20 milligram. We also had that after the modification, the mean value of coating weight dropped to 1.36 milligram with standard error 0.24 milligram. So now we continue doing the galvanostatic test. We start to see that there is a fluctuation in capacity performances between the coins. And this is expected, and statistically that spread should be correlated to the standard deviation of our set of 5 coins. And we can calculate the standard deviation and see if it matches the result on the potential stat. So the standard deviation will be square root 5 times larger than the standard error. So in the before set, sigma b becomes square root of 5 times 0.20 milligram, which is 0.45 milligram. And this gives us a relative uncertainty in that coating mass to be 0.45 milligram divided by 2 milligram, which is 22%. And hence, since the capacity depends on the relative uncertainty in the coating mass, we will expect that the cells in capacity will have a spread that is 22% fluctuation. We can do the same thing with the modified coin set, where we modify the electrode material. Square root of 5 times 0.24 milligram, which was the standard error, we get 0.54 milligram. We calculate the relative uncertainty, which is 0.54 milligram then, divided by the coating weight mean value, which was 1.36 milligram. That is 40%. So here we can see that when we're doing the potentiostat galvanostatic measurements on the modified coin set, since it's a little bit lower coating weight on that and a little bit larger standard error, the standard deviation becomes larger in the coins, and that spread in capacity now becomes 40%. So to continue now, let's pretend that the reference set, the before modification set, is standard graphite electrode material. That is about 310 milliampere hours per gram as specific capacity. So in the modified set, the A set, let's pretend that that has an improvement that is 75% more than just the regular graphite. Since we're measuring absolute capacities, the thing that we will see, the spread will look like this table. So here we see the capacity in microampere hours for the before, the B set, before modification. We're measuring 450, 540, 615, 685 and 810. And in the coin sets with the modified electrode material, we're measuring 375 microampere hour, 525, 717, 889 and 1183. And as I said, we would have a larger spread in the A set. We see that in the data here. And we're also measuring capacity, right? Not specific capacity. So we're measuring that current versus the current times time, right? The full before after test how to. Step 5, absolute capacity calculations. So now we have these two data sets. Set B before electrode modification and set A after that electrode modification. We can do standard statistical calculation. We calculate the mean value of each of these 5 coin sets. And then we get that the mean value of the capacity before modification becomes 620. And we also get that the standard error is 62 microampere hours. And for the modified A set, mean value of capacity, the absolute capacity, is 738 and standard error 141 microampere hours. And we must understand at this stage now of the presentation that this spread is caused by the uncertainties in the coating weight. It's very important that you understand this and you don't think that this is caused by faulty readings on the instrument or similar types of errors. Most likely we will also see a slightly larger spread, and this is because of these other uncertainties, but those will not influence us much, so we don't have to go deeper into that in this presentation. You can also see this important observation here, because if we look on that modified A set, we can choose our so-called typical sample here, 1183. That's a lot, right? So that is almost doubling the performance of the values we see in the B column there, right? So that means if we only publish one result, we choose 1183, and then we think that these other values, especially the top one here, in the modified set that says 375. That is less than all the values in that reference set, right? All the values in the B set is higher. So here is this, what shall I say, faulty mistake that you think 375 must be a false reading, and then we throw that result away. And then we cherry pick 1183. So that is something we should stop doing now, right? Because that is fraud. So the next step is to calculate specific capacity. So now you have a choice. Do you do A, divide each of these cells that we have measured the capacity for with the calculated coating weight of each cell? Or do we divide the measured mean capacity with the mean coating weight? If you answered A, you are doing it wrong. We should absolutely have no more of that deadly error tree stuff, like that we do cell 1, we take the coating weight minus the mean substrate weight and things like that. From now on, individual cell performances has no further useful meaning. It is the mean values we're going to use, and only mean values in the same calculation. Never mix single sample data with mean value data. The full before-after test how to step 6, specific capacity calculation. Alright, so now we have measured the absolute capacities with standard error calculation. So we have that the mean value of the absolute capacity of the before modification of electrode became 620 microampere hours and standard error of 62. That is per coin, so to say. I mean, the absolute capacity of the coin, the actual coin, mean value. And the modified electrode set, we get the mean value capacity to be 738 with standard error 141 microampere hour. And as we talked earlier about, we have that the specific capacity, CS, is going to be calculated. So we get that the mean value of the specific capacity will be the mean value of all these absolute capacities we're measuring divided by the mean value of the coating weight, right? Only work with mean values now. And here we see that the capacity, as we talked earlier about in the potentiostat and galvanostatic cycling, will be a fixed current times a mean value of times that we're measuring. That is actually how we're measuring capacity. So it will be mean value of time divided by the mean value of coating weight. So standard error calculation, the combined standard error for this will be the mean value of capacity times that relative percentage number of error of the combined relative standard errors, that Pythagoras thing, right? And since time had great accuracy on electronic devices like potentiostat, this term will be 0. We can approximate it to 0 under that square root sign. So that means we only have one term left to consider, which is the relative coating weight. Hence, we come to the conclusion that this relative error in measured specific capacity will be the same as the relative error in the coating weight, right? So once again, we want to know the combined standard error because we want to do the comparison of specific capacity before and after, right? So the combined standard error in this case will be the standard error that we have for the after modification. So that, and we know that the standard error of after modification will be, here we see it's the relative error first in coating weight, standard error of the coating weight divided by the mean value of coating weight. That is a percentage number, right? Times that mean value of specific capacity, right? Then we get the standard error of specific capacity for the after test set. And the other term is the same thing, the relative percentage in uncertainty of the coating weight of the before the B coin set times the mean calculated mean value specific capacity of the B set. Sum those two together in square and do the square root of those, right? That's what we want to do. The full before-after how to test step 7. So, specific capacity comparison test now. So now we want the combined standard error. We want to test, is there actually a significant difference between these two? So we want to do the mean value of the measured specific or the calculated specific capacity for the after set, after electrode modification, minus the mean value of the specific capacity for the before modification set. We already shown how to do the combined standard error of that, the difference. That is that sum of that Pythagoras of each standard error of specific capacity. And now we know, same thing as before, that the difference between the mean values of calculated specific capacity must be larger than 2 times, because 95% confidence, times the combined standard error. But here we can do a simplification. Since the measured specific capacity after modification, we at least expect that to be larger, and we also showed in the data it is larger than the before modification specific capacity. Then this criteria that we must fulfill to say that is statistically significant, we can simplify that by replacing the before mean value specific capacity to be the same value as the specific capacity afterwards. That will increase the combined standard error, so it becomes larger, right? So that means the criteria we're fulfilling will be harder to fulfill. So from the question to determine if it's statistically significant, if we fulfill this criteria, then we definitely fulfill the true criteria, right? But the smart thing by doing that is we see that we can break out the mean value specific capacity for the after set, right? Outside the square root sign. So, and if we do that, we can put everything together in the same equation here, and then we can divide by that mean value specific capacity of the after set. So we get that on the left side of this comparison equation. So what do we have on the left side now? So on the left side, it says that the relative increase in performance, that is the top here, how much it increase relatively to the after set's mean value specific capacity. Normally when we talk about percentual increase of something, we always divide by the original, the B set in this case. But here we actually divide by the A set. It becomes like that in the equation. So we need to remember that it's not like a real percentage improvement. Actually what the rate is saying here is that we have changed the viewpoint. So we're actually asking how much worse in percentage is the original reference set compared to our new modified set. That is actually what it says, this rate here. And that ratio must be larger than 2 times the square root of the combined relative errors of coating weights. Sum them up in square, right? The full before-after test how to step 8. Comparison test calculation then. So, now we can insert our absolute capacity data, right? We had that before sets absolute capacity was 620 microampere hours with standard error 62, and after set was 738 microampere hour with standard error 141, right? We do the specific capacity calculation by division of the mean coating weight. So then we get the specific capacity of before modification of the electrode becomes 620 microampere hours divided by 2 milligram. That gives us 310 milliampere hours per gram, which is the expected theoretical value of that original graphite electrode, with its standard error of 31. And for the modified set, the A set, that specific capacity becomes 738 microampere hours divided by 1.36 milligram, which was the mean coating weight, and we get the specific capacity for the modified set to be 542 milliampere hours per gram with a standard error of 130. So that's almost twice, not really twice, almost twice. Then we insert these two calculated specific capacity values into our comparison formula here. So if we look on the right side and do the relative combined standard error calculation, we see we take 2 times the square root of the individual relative errors. And we have for the first B set, we had 0.20 milligram divided by the mean coating weight of 2 milligrams. So that was 10% relative error. Take that in square and we add that to this other relative error, which was for the after modified set was 0.24 milligram in standard error divided by the mean coating weight 1.36 milligram. All that, sum them up, square root of that times 2. Then we get 40%. So that means that the improvement to be statistically significant must be larger than 40%. Otherwise, it's not statistically significant, that increase we're demonstrating. So the left side of the equation, we do that ratio of improvement of capacity, that relative improvement, the boost as we tend to call it. 542 milliampere hours per gram minus 310 milliampere hours per gram divided by that performance we have in the modified set, 452 milliampere per gram. That becomes 43%. And 43% is larger than 40%, and thus this means it has passed the significant test. Barely, 43 is not so much more than 40. But this is a statistically significant proof that our modified electrode is actually better than the original one, right? And all these measurements was done where we had this coating weight of 10 grams per square meter, and it dropped a little bit to 6.8 in the modified set. But this answers the question 1, right? How much must the performance boost of modification have to be significant? So this equation we have in front of us answers that. So now we can clean that up into a general statement. The full before-after test how to step 9, the comparison test rule. So if we assume a relative coating weight uncertainties between before and after set to be about the same, then we can simplify our previous equation further. So then we get that the combined standard error will be 2 times the square root of the standard error divided by the mean value of coating weight. That is the relative error in coating weight for the A set, plus this relative coating weight of the B set in squared, and all that under the square root sign times 2, right? This can be simplified. So if we have that the standard errors is the same for both sets, those relative errors, then we see that the square root basically becomes just a square root of 2 factor. So then we get 2 times the square root of 2 times the relative error in the A set, since it's the same as the B set. That's what we are approximating here. And square root of 2 times 2 is about 3. So then we see that the criteria that we need to fulfill says that we must be 3 times better in our performance boost than the relative error in the coating weight. That's what this equation says. So we call that equation 1a now. And we also say that the relative performance boost, we give that a variable called the x percentage. So the x percentage must be larger than 3 times the relative error of the coating weight. That is a very interesting general statement, right? Since the coating weight in the A set is calculated from the coating coin mass, the full coated coin mass, minus the substrate mass, right? Then we can put that into the same equation. So that relative error we can rewrite as the square root of the standard error of the coated electrode mass plus the standard error of the substrate mass, both in squared, of course, and square root of that. And the coated weight is, of course, the difference between the mean values of the coated mass electrode coin minus the substrate mass of the coin, right? The full before-after test how to step 10, the comparison test rule. So question 2 then, how much coating weight do my electrode needs to have to statistically be significant to prove a X% boost increased in performance, right? So that is the reverse, right? The first question was, how many percentage in improvement do I have to if I know the coating weight to be statistically significant? Now we asked the reverse. How much must the coating weight be if I know how much the increase is? So we can answer this. So let's continue, and we can do the ideal case. So if you look on the standard error of the coating weight, that is the sum of standard errors of the substrate and the coated coin square root. That is larger, of course, than if we assume that the standard error of the coated coin is the same as the standard error of the substrate. We saw initially of this presentation that the standard error of the substrate was about 4 times less. And we cannot get a better standard error than the substrate we are coating onto, right? On top of. So an ideal case where we have a perfect coating, then we will inherit the standard error of the substrate that we're coating onto, right? So the standard error of the coating weight ideally can never be better than square root of 2 times the standard error of the coating substrate. So if we put that into our relative coating weight uncertainty, then we see that we can describe that as square root 2 times the standard error of the coating substrate divided by that mean value of the coated mass minus the mean value of that uncoated mass coin. So a copper foil is 25 micrometer in thickness, and that has a standard error of 0.012 milligram. That was the histogram we showed in the beginning of this presentation. And that is given for a set of 100 coins, and they are 60 millimeter in diameter. So a 5 coin set, we can statistically expect to have a standard error for 5 coins. We can calculate that. So we first calculate the underlying standard deviation, which is square root of 100 times larger, 10 times larger than the standard error. And then we divide that with the square root of 5 to get the standard error for 5 coins. And that is 0.053 milligram then. So, and if it's 60 millimeter coins, we can convert that to grams per square meter by multiplying by 5. So, if we do that and insert it into the equation above, we see that the boost performance in percentage, the X%, must be larger than 2 times the square root of 2 times the square root of 2 times 0.27 grams per square meter, where 0.27 grams per square meter was that standard error for 5 coins, 0.053 milligrams times 5, right? So this gives us the equation 1b, that the coating weight must be larger than about the inverse of the boost performance in percentage. So that means if the boost performance increase is 10%, then 1 grams per square meter divided by 0.1 becomes 10. So that means we need 10 grams per square meter in coating weight, in mean value of coating weight, to prove a 10% boost. The full before-after test how to step 11, the golden rule. So we had equation 1b that said that the mean value of coating weight that you need must be, in the ideal case, when your coating has the same standard error as your substrate of the copper foil, then that coating weight must be at least the inverse of that boost performance increase. So if you have 10% boost in performance increase, 1 divided by 0.1 will be 10. So then you will need 10 grams per square meter in coating weight to be able to prove such a small boost. And that is under these ideal conditions, as I call it. So if we take equation 1b, then we see that that is like a direct consequence actually of equation 1a. So if we rewrite 1a, we can get equation 1c. That says that the mean value of the coating weight must be 3 times larger than the standard error of the coating weight divided by the boost performance in percentage. So if we are not in like an ideal theoretical case, so under practical normal conditions, we know that the standard deviation sigma for the coating weight is about 0.45 milligram. And that is for this with a typical 5 coin set. Then we see that the standard error with that type of standard deviation, then the standard error for the coating weight becomes 0.20 milligram. And that corresponds to 1 gram per square meter. So we get that the mean coating weight must then be at least 3 times the inverse of the soaked relative performance boost. So the mean coating weight must be 3 times the standard error of the coating weight divided by the boost performance. But since the standard error under normal condition is about 1 gram per square meter, then we get this rule 1b that says that the coating weight must be larger than 3 times divided by the inverse of the boost percentage. So instead of having 10 grams, we can prove a boost of 10%. We must actually have a 30% boost if we have 10 grams of coating weight per square meter. So now comes the final part. We, in the above equation, we can substitute the relationship between the standard deviation and standard error. We know that the standard deviation is the square root of number of samples times larger than the standard error. So we insert that into equation 1b, and that gives us the golden rule, as I call it. And the golden rule states that the relative performance boost must be at least 3 times the relative uncertainty in the coating weight of the cell. And the criteria limit scales down by 1 over the square root of number of samples in the cells being tested, right? So here we see the boost increase must be 3 times larger than the standard deviation of the coating weight divided by the square root of number of samples in your set, and the coating weight's mean value. We call this the golden rule. The full before-after test how-to step 12, the golden rule continuing. So in the golden rule we just derived, we see that the criteria limit drops by 1 over square root of n for the number of cells being tested. So into this rule we can put in that normal conditions that we have when the standard deviation is 0.45 milligram, which corresponds to 2.2 grams per square meter. So let's insert that into the golden rule. Then we see that the boost performance in percentage must be larger than 3 times 2.2 grams per square meter divided by the square root of number of cells and divided by the mean value of coating weight. So then we can do some calculations on that. So at normal coating weight of 10 grams per square meter, if we insert that into the formula, then we can calculate what is the boost improvement in percentage we need to have for it to be statistically significant as a function of the number of cells we are testing. So then we see, if there is only one single cell tested, 66% boost is the value we need to pass for it to be significant, right? So this number you can actually use when you look on those already published paper. They only have one graph of capacity, performance, measurement, and so on. And if they don't even mention a standard deviation, which they mostly don't do, right, because they only have measured one sample, right, then we can assume that they are under normal condition and we can use this standard deviation. And that means that if they don't come above 66% performance boost, then that whole paper is bullshit. That's what that means. And we see that the requirement drops for 2 coins, it drops to 47%. 5 coins, which is our best practice, as we say, that we want to aim for in our test, we see that we must at least show 30% boost. So the higher up you go, I mean, if you should manage to do 100 coins, then you actually can prove 6.6% in increase, right? So that's very impressive. But we can also reverse the equation of the golden rule and say that, let's say we want or have a 30% boost. We expect that. What would the coating weight then be as a function of the number of coins we're testing? So then it's the same thing. If there is a single cell test only, so if you see a paper saying that it's showing 30% boost performance, well, if they only have one single test, then they need to be about 66%, right? If they have 10 grams. But if we do the reverse calculation, say if they have 30%, then they must have 22 grams of coating weight for it to be statistically significant. If we do 2 coin cells in the test, it drops to 15 grams. And our best practice 5 cells, we see we need about 9.8 grams or 10 grams per square meter in coating weight for a 30% to be significant boost. The summary. So, the golden rule comparison of sets that I have demonstrated shows that the relative performance boost must be at least 3 times the relative uncertainty in the coating weight of the cell. And this criteria scales down by 1 over square root of n, where n is the number of samples being tested. That is the golden rule. And the performance boost x in percentage is defined as the mean value of the measured capacity, specific capacity, after the modification of the electrodes have been done, minus the mean value of the specific capacity before the modification. So it's the difference between those two tests, sets that we test, divided by the modified specific capacity and not the initial reference. That's important. This is how we define the X percentage here. So it's not a regular percentage improvement. It is in this perspective that how much worse is the reference compared to the improvement. That's what the formula actually says. So, as a last summary, best practice to implement for you in your research. You shall run 5 modified cells and 5 reference cells. Do not use theoretical reference values and so on. Make 5 reference cells and 5 modified cells. Run them in the potentiostat and compare. When you're doing 5 cells in each set, you need to compensate standard error with the calculations with the student t factor. That means you multiply the calculated standard error by 1.14. And then you use 95% confidence interval, the 2 sigma thing, only in the last step of your calculation. Otherwise, you shall stay in the 68% 1 sigma domain. And the 4th best practice is don't go below 10 grams per square meter in coating weight. Try to stay on 10 grams. That is a good number. If you fulfill all this above, then that implies that if your measurement shall be significant, then with 5 cells in your sets and you have 10 grams per square meter in coating weight, that gives you enough statistics to say that for all capacity boosts found, that must be larger than 30%. If they are that, then they are significant. So that concludes my presentation. I hope you really like this and that you learned actually a lot about measurement uncertainties and statistics in general. And this is very important for you as a researcher to understand, and especially that you must publish the uncertainty together with your result in your publication. And I think this golden rule will be of great help when you're doing your lab work. So thank you very much.